So welcome back friends. So in the last section I gave you the reasons why we should study relativistic quantum mechanics. Two main motivations are essentially say that from astroparticle physics side I talked about the 21 centimeter line, and the second one was on graphene side in the condensed matter physics systems essentially. So now just before starting the writing down the first relativistic quantum mechanical wave equation, okay, I just want to mention a couple of points which we were talking yesterday essentially. Okay, meaning in the previous lecture. So we were talking about that there are fundamental constants in relativistic quantum mechanics in the quantum mechanical regime. So normally quantum mechanical regime has H cross, okay, and then relativistic regime has C. So in the relativistic quantum mechanical regime you should find both of them essentially. So relativistic this I think I mentioned in the previous lecture too, but it is okay to repeat a couple of things essentially. Relativistic QM case quantum mechanics space you will find both H cross and C, that is the basic idea. So what are the implications of this? So things we know about quantum, and we want to keep the same quantum mechanical structure as we have revised essentially, same thing like in terms of vector spaces and so on. So and we will assume that quantum mechanics will exactly work in the same fashion as we have worked in the Schrodinger equation, and then we will see the pitfalls of it and various things. But let us, for the starting point, it works very well. Let us just say that it is a very good strategy to assume that the entire thing about quantum mechanics, the postulates, the potentials and the Schrodinger equation and so on, so should work in the same way. But immediately we will see a couple of things. One is measurement bound. So according to the first, I think the first lecture itself we talked about the uncertainty principle in quantum mechanics. So according to uncertainty principle we have delta px delta x should be around H cross. For this, okay, so delta px and delta x should be around H cross, and there is a corresponding uncertainty principle for the energy and time. Okay, so this is delta E times delta t is again is equal to H cross. Now what is delta t? Delta t is essentially the time required to make a measurement of a system essentially. So if you want to make a measurement on the quantum mechanical system, you have to make an interaction. So the time interaction time required to make a measurement essentially, delta t is essentially the interaction time okay. Now this you can write in this particular fashion. So if you say delta E, okay, is nothing but V delta P, okay, V delta P, and so we re-express the uncertainty in energy in terms of some the velocity times the uncertainty in momentum essentially, okay, in terms of the product of these two. So the entire thing, okay, can be written if you make at the velocity difference at 2 points, essentially v minus v prime time delta p delta t is equal to h cross. Now what I am saying is that delta delta the answer the velocity can be measured in terms of v minus v prime, essentially, where v and v prime are the measurements made. So two measurements made, essentially v and v prime are the two measurements made. The difference between the two measurements times the uncertainty in the momentum times the uncertainty in the interaction time to make a measurement, essentially. Now as delta p goes to 0, what we have is v prime minus v should goes to infinity. V prime minus v should go to infinity, because as we can see from this equation, h cross is always a constant. As delta p goes to 0, one of them should go to infinity, such that, or go reach to infinity, essentially. Now imagine that v minus v prime, or v, or the velocity, if you are sitting in this is what happens. This is what happens in classical systems, or no, we should not use the word classical, we should use the word non-relativistic quantum mechanical picture. In the relativistic quantum mechanical picture, the velocity of the particle is c. So that means velocity of light in vacuum comes in play. Okay. In the non-relativistic quantum mechanical picture, v is classical, delta p is the uncertainty, and the difference between the velocities, or the measurements of the velocities within the time scale of delta t, essentially within the will go to infinity. In the limit, the uncertainty in delta p is equal to goes to 0. In the limit, the uncertainty in the momenta goes to 0. But in the case of relativistic systems, the velocity of the particle is the velocity of light, essentially. In such case, what happens is the momentum uncertainty times then the time difference uncertainty is given by h cross by c. Okay. So you have this new relation, where both the fundamental constants will play a role, that you cannot, by making a measure okay, where both the fundamental constants play a role as I promised in a relativistic system, essentially. So in a relativistic system, you have this new relation delta p, instead of delta E delta t is equal to h cross, you have delta p delta t is going to h cross by c, essentially. It is the same relation, but except that velocities are said to be relativistic, essentially. Okay. So this is so if you want the uncertainty in the momenta and the uncertainty in the time, essentially the product of these two uncertainty should be h cross by c, Now you have a something similar relation in the position coordinate also, which plays an extremely important role. So this comes from another important effect, essentially called Compton, sorry for the wrong pen, yeah, it is called the Compton wavelength. Now you can derive the Compton wavelength of the particle by saying, so let us start with the uncertainty relation delta p x is equal to h cross. In a relativistic system, the uncertainty in the momenta, if you take in terms of the mass of the particle, essentially is mc in terms of the mass of the particle, because V is nothing but c, essentially V is nothing but c. So now this gives you a new wavelength of the particle, which is nothing but the uncertainty in its position, okay, h cross by mc. Okay. This is called the Compton wavelength of a particle. So every fundamental particle which is relativistic has an associated fundamental wavelength associated with it, which is called the Compton wavelength. Every fundamental particle has a fundamental wavelength associated with it, which is called the Compton wavelength, and that tells you what is the what do you call the uncertainty, this uncertainty which you cannot escape, which it cannot escape, okay, which is associated with its moment, with its mass, and given by the two fundamental constant h cross and c, okay. This particular wavelength is called Compton wavelength. So the Compton wavelength is one of the fundamental properties of any particle. The point of this Compton wavelength tells you that, okay, Compton wavelength tells you that at what distances, or just like this measurement bound tells you at what momenta relativistic quantities will become important, okay, at what momenta the relativistic calculations are important, okay, the relativistic effects are important. This sets the bound, essentially at what momenta, depending upon the time scale of the measurement, at what momenta the relativistic effects will take over. In a similar sense, this tells you at what distance scales the particle, the relativistic effects of this particle will be very important, essentially. So below this distance scale, the relativistic effects are extremely important, and the non-relativistic quantum mechanical picture which we studied will no longer be valid. So these are your sort of your bounds in momenta and your and in your position, okay, which give you an idea that how to where, okay, these bounds give an idea as to where at what regimes, okay, in position and momentum relativistic effects are important. Okay. This tells you precisely, okay, well, approximately what regimes when the relativistic effects become important, and more importantly non-relativistic quantum mechanics fails. So if you are in the regimes, which we have talked about several regimes essentially all through this lecture, okay, if you are in the regime where the position where we are below we are measuring properties of the particle below its Compton wavelength, the relativistic effects of the particle becomes very important, okay. Say for okay, and I can give you several examples, but we will come to that later on. Similarly, if you are dealing with momenta which are delta p around delta t is around h cross dot c. So then in that case also this is generic, essentially, that you will end up having um, relativistic effects which are extremely important, essentially. Now for example, in the quantum say for example in scattering of particles, essentially. So you can have non-relativistic scattering and relativistic scattering. Say for example below the Compton wavelength of the electron, essentially the relativistic scattering effects of the electron are extremely important. If you are just shining, if you are just hitting photon with a light, photon with on an electron, say for example, okay, you cannot no longer use non-relativistic scattering cross sections below the Compton effect, essentially below the Compton wavelength of the electron, essentially. So this is one thing, okay, which we have to keep into consideration while demanding that all the ordinary quantum mechanics should work in the same fashion in the relativistic regime also. So this is one of the main thing which okay, is important if you want to study relativistic quantum mechanics case. There is also another feature, another thing which is important, essentially. Okay, another feature which is important is I just want to emphasize that we are in the relativistic quantum mechanics case. Okay, okay, we are in the relativistic quantum mechanics case, and what we are looking at are so assuming that if I just blindly assume that these are the only things, meaning all the postulates and all the framework of the quantum mechanics flows through, the first constraint we get is from the uncertainty principle, essentially. Okay, and that leads to these questions. And the second second constraint, or the second feature which we had to keep in mind always, is linear operators. Now in non-relativistic quantum mechanics we are constantly used to the concept of linear operators. Say for example we have P cross is equal to minus IH cross del and E is equal to IH cross del T, and okay, we say that I have E is equal to P square by 2m. This is quadratic, but still the operator is quadratic, essentially, but this still gives you a linear equation, essentially, or okay, del by del T psi h cross square by 2m psi, and this is nothing but your Schrodinger equation. Which we have done already several times. So if I just assume the quantum conditions, essentially the P is in terms of operators, P is nothing but IH cross del and E is equal to IH cross del by del T, and put it in non-relativistic NRQM quantum mechanics, I get back my Schrodinger equation. Now the time evolution, what is linear? The time evolution is linear because it is only 1 power of t. So we are typically used with time evolution is linear in NRQM. Okay, the time evolution is linear. There is only one particular power of time. Okay, now this helps you also. Okay, the second thing is the differential operators. Now you see, let us see how to point out. Okay, so for example, okay, this is 1 power of t, this is 1 power of t, this is 2 powers of derivative operator, this is 2 powers of derivative operator, this is 2 powers of derivative operator. Okay. So, 2 powers of derivative operator, but then they are linear operators. So, what happens is now if you take d square a psi 1 acting on a wave function plus b psi 2, this just becomes a d square psi 1 plus b d square psi 2. So, this is just a linear operator. Good, but in the relativistic regime this entire thing completely modifies. Okay, we have to get used to dealing with operators if you want to think seriously. Okay, let us see. Okay, let us see what happens in relativistic case. In the relativistic case, what happens? E square is equal to p square plus m square. Okay, I am just setting again p is equal to 1, c is equal to 1, h cross is equal to 1 and everything. So, what is E? E is equal to root of p square plus m square. See this is inherently nonlinear. Okay, this is inherently nonlinear. Okay, this is inherently nonlinear. How will you deal with it? What we will have? Say for example, now if I write it in terms of differential operators. So, okay, if I write it in terms of differential operators, so p square is equal to h cross del and so on. So, E is equal to square root of d square plus m square, where d is equal to minus I h cross del, del, say for example. Now, this is equal to d square plus m square whole power 1 by 2. Now, this is can be expanded. Now, what you will get? You will get all powers of d square plus d power 4 plus d power 6 plus so on. So, what you end up having is series of higher derivative operators. Now, what is the problem with higher derivative operators? If you have higher derivative operators, so you can imagine that this will end up being having, so instead of you do not have local theories, so you will have something called non-local theories. So, what is, so this is nothing but you can express this entire thing as I is equal to 1 to n some del square by del x square. Now, these are inherently, because they are non-linear, so you can have, you can start looking at effects which are very far away from x0. Essentially you can think of that something. So, you are taking derivatives, second derivative, third derivative, fourth derivative, fifth derivative, nth derivative. Essentially you are looking very far away from the point essentially that you do not see. Okay. Okay. These are set of nonlinear differential operators, and first of all this will lead to non-local theories. What are non-local theories? That means you see the effect of something very far away, like it is like essentially a non-local effect. So it is not at the same space time point. So you are seeing the effect of some other space time point at this particular space time point without any propagation, without any effect of that information being passed from that particular point to this particular point essentially. So these are called, like it is like in the classical physics, this goes under the name as action at a distance, right, for example. Okay. So you know that magnet will repel another magnet because there is even at a distance essentially. But such action at a distance theories do not work, okay, do not work in quantum mechanical regime essentially. So these theories are inherently unphysical, okay, you cannot make predictions and anything, you cannot do any calculations. So these are critically unphysical theories. You cannot do, okay, calculations, and there are many other properties which you will see at a higher level essentially in a completely in a field theory point of view. If you put in fields with action at a distance instead of just particles, essentially you will have lot more problems essentially. So you do not want action at a distance in quantum mechanical regime. So in quantum mechanical regime it means that you have propagations which are superluminal, and you are breaking all the tenets of special theory of relativity essentially. Okay. So these are unphysical theories, these are unphysical theories which lead to unphysical properties which are there, and you cannot solve them. Most of them they do not have any solutions. These are no, you can only, they do not have analytical solutions. If you want to solve this kind of bunch of equations, you do not know where to truncate the series, and so there are all these problems associated with higher derivative theories essentially. So higher derivative theories are not attractive, okay. Are not attractive, and also not desirable because of a host of problems. So this is one thing which we have to keep in mind, that you cannot take the square root and then try to solve, and because solutions will require a lot of degrees of freedom somehow. So you have to put in more and more degrees of freedom, and then you have to regularize the theory somehow, and then there are nonlinear differential equations which do not have analytical solutions, and so you may have to solve them numerically. So all these problems are there essentially, you may not have known the solutions and everything, okay. So you have to keep these two things in mind before proceeding further essentially. So one thing is associated with the bounds on measurement coming from the uncertainty principle. Second thing is the very structure of the energy momentum relation in relativistic theories, that E square is equal to P square plus Pm m square, and if you want to write them in terms of a square root, that leads to a lot of problems, okay. So with this in mind, with the last 1 or 2 minutes essentially what I will leave you with, which we will take off in the next class, is the first relativistic wave equation which we will write down, okay. And this equation, okay, is called the Klein-Gordon equation. This is called the Klein-Gordon equation. This was incidentally actually discovered first by Schrodinger, okay. Schrodinger actually discovered it, okay, but he did not publish it because he thought it is relativistic, so it may not be applicable for a hydrogen atom. So he discarded it, and then he went for the non-relativistic case, which led him to derive the Schrodinger equation of the non-relativistic. So what is the Klein-Gordon equation? The Klein-Gordon equation is now nothing but E square is equal to P square plus M square. You do not take the square root, you live with the two derivatives in time and also with the double okay, and you know d square is anyway is linear essentially, you live with it, you do not take the square root and you just write down the operators. E is equal to putting back this to both equations. So this gives me IH cross I but anyway now we are taking H cross is equal to 1, this gives me now all this should act on some particular object which we call the Klein-Gordon equation, which we call the Klein-Gordon field or Klein-Gordon wave function. So this is nothing but your Klein-Gordon wave equation essentially. So this is the first relativistic wave equation which you are seeing essentially. So this you can write, you can put the del square along with the t square, and you can write it as box plus m square phi is equal to 0, where box is equal to del t square minus del square. Okay. I should make a small correction here essentially. Okay. So this is called the D'Alembert operator. This is called the D'Alembert essentially D'Alembert operator. So finally we have first wave equation we have seen, it is relativistic, it is for quantum mechanical particles, and so in the next class onwards we will start looking at its first solutions and the implications of these solutions and various features associated with this particular this particular field essentially this particular particle. So we have introduced ourselves today the Klein-Gordon equation. So I will stop here and we will see in the next class what are its solutions and the features of it. Okay. Thank you.